All right, so we're just going to continue the process of yesterday, trying to get a little bit better at understanding how we need to analyze these problems and go about answering them. The major skill from yesterday is this whole, hey, you've got a force here, it's A. You've got a force here, it's B. You've got a force here, it is C. Okay? And then I say, what is the sum of forces in the X and what is the sum of forces in the Y? Let's run through that just very, very quickly here. What is the sum of forces in the X here? Positive A. Negative bx. Negative cx. Very good. And what's the sum of forces in the y? Oh, I'm assuming that's perfectly. So positive by. By and? Now you're never going to see A, B, and C in our particular examples because we've already got those labeled. The idea that we're transitioning to yesterday was this idea that we don't need to put A and B and C on these. We already have labels for them. This is the mixing of that force diagram situation with all the others. So we pulled Kenzie in a chair, yes? You're going to have to remind me of some numbers here because they are a little bit different than first hours and I don't remember. Mass? 68 kilograms. Very good. I think we called it tension. Force tension on her when she was at constant. 9 pounds. All right, and then we'll hold off on the other one for a little bit later. What was the force diagram on her as she was at constant velocity? Gravity down. Normal force up, which of course could be seat on person if you prefer. And force tension which way? Forward, to the right in this particular case. And again, force tension you might have labeled as scale on person or something. That's also completely fine. And force friction back. How should force friction relate to force tension? Should be the same. How do we know? She's at a constant velocity and therefore forces are balanced. The question in this play here was, what is force normal and what is force friction? Not here right now. Thank you. All right. So, before we left, I was talking about what if we dropped Kenzie off the side of a building? Okay? And the force diagram on her was force of gravity. Now, so we somewhat understood that, but I want to try to add a little bit to that by doing another quick demo here, not demo, but another quick example that I think definitely helps. Imagine that you're an astronaut here in space, okay, and you are going to push a small mass, okay, specifically a mass currently at 1 kilogram. The idea is you need to understand what force actually is, or how it's defined. Force is defined by what it's able to do. Meaning, if I take that mass and I accelerate it at 1 meter per second squared, how much oomph does that take? What's that? Takes 1 Newton, correct. Takes one Newton, 1 kilogram meter per second squared. So if you had to guess then, how much force does it take to accelerate it at 2 meters per second squared? 2 newtons. And I don't know, let me pick another arbitrary number in this particular case. Let's go ahead and say, like, how much oomph would it take you to push this to accelerate it at, I don't know, 9.8 meters per second squared? 9.8 newtons. Obvious stuff. Sure. Now, it's not me pushing at all. What's pushing on this as it sits in my hand? This 1 kilogram. Earth. Specifically, gravity of Earth. And how much will it accelerate? 9.8. And as this is 1 kilogram, and it will accelerate at 9.8, how much oomph is the Earth pulling on it at? 9.8 newtons. That is how much the thing weighs. That is its weight. How much the Earth pulls on it is its weight. Now, is it currently accelerating at 9.8 newtons? No, how come? I'm stopping it by using what force upwards, actually? Nope. Be friction, yes. It would be surface friction. My fingers are pulling upward. And guess how much my friction is pulling upwards at right now? So it weighs 9.8 newtons. So my hand is pulling up at 9.8 newtons. Yes. Now, how would this change then? Okay, if instead of 1 kilogram, we are now trying to accelerate 2 kilograms. And by the way, for sake of simplicity in math, real quick, let's go ahead and I'm going to transfer back and forth between g being 9.8 and doing the whole multiple choice thing of g being 10, so you can do the calculation quickly in your head. So let's just go ahead and say for right now, yes, if you do problems, always 9.8. But when we're talking about just kind of quick and dirty calculations like this, let's just go ahead and say 10. So in other words, let's go back. If I said this is 10 instead, it's not, but it's 10. Okay, how much does the 1 kilogram weigh? 10 newtons. So how much does 2 kilograms need to be pushed in order to accelerate at 9.8? 20. You get the idea. What simple thing are you doing in your calculation in order to figure out how much the thing weighs? Multiply it. In other words, you're finding the force of gravity by taking the mass and multiplying by g. Yes? The reason that works, again, going back a little ways here, is this. Technically, the real law is Newton's second law. But what we said is, if Kenzie's only force is force of gravity, we know that she will accelerate at 9.8. So if that is this, then that is this. Yes? But do we actually need to drop Kenzie off the side of a building in order to know that this is going to be the case? No. And is this force here, that she was dropped off the side of the building, the exact same force as this one over here? Yes. So can we calculate for force of gravity only what this number is, even though she's not accelerating? I mean, how much is she going to accelerate in this example? 0. She's going to accelerate at 0 in this example, 9.8 over there. But it's just like me holding up this mass right now. Do you need me to actually drop it to know it's going to accelerate at 9.8? No. So you already know the force down is 9.8. So you know the force up is 9.8. How can we figure out her force of gravity here? Fg equals mg right over here. How are we doing? Okay, we're going to take that. I'm going to take it one step forward in order to calculate this right here. Now I'm going to tell you right now, the calculations I'm about to show you, most of you are probably going to roll your eyes and be like, you seem like you way overcomplicated something that we already knew. Okay? For example, I'll just start with this. Hey, tension's 9 pounds. Okay? Pretty sure without any level of calculation whatsoever, you should right now be able to tell me how much force friction is. How much is force friction, guys? 9 pounds. Yes, super simple stuff. And I don't want you to lose that level of intuition, but also what I want to give you is a kind of a tool to analyze this that does the exact same thing. So here's what we're going to do. We're going to sum the forces in the y. But just like we did on the very first thing, we're going to sum the forces just like we did here. Except Newton's second law tells us that sum of forces is equal to mass times acceleration. And since this is just in the y, we're just worrying about this in the y. You are always going to start at Newton's second law. After starting at Newton's second law, you will always do the same two things. Ask the exact same two questions. The first question, and you can go in any order, okay? I'll go left to right to start off with. I usually go right to left, but that's just me personally. The first question is, what is the sum of forces in the y? In other words, look at your force diagram and do exactly what you did over here. Look at each force and go, is it in the y? Is force normal in the y? Yes. Is it positive or negative? Is it only in the y? Yes. So we write positive force normal instead of positive A or positive B. Okay? Next, is force friction in the y? No, skip it. It's force tension in the line. No, skip it. It's force gravity in the line. Yes, is it positive or negative?
Negative.
Is it only in the line?
Yes.
Yes, so I write negative force gravity. And there's no other forces, so I'm done. I have now summed the forces in the y. That's the first of two things to do. The second one is relatively easy, which is why I usually start with it. Is it accelerating in the y? No. She's not accelerating in the y, so that means acceleration in the y is 0, which if this is 0, so is that. I'm going to cancel this whole thing out to 0, and it's equal to 0. Very common question is, can't I just start at 0? Yeah, but again, we want to make sure that you're always starting from this understanding of why things are the way they are.
Wait, why is acceleration 0?
Well, you saw her, right? Was she accelerating up or down when I was pulling her at a constant velocity across the room? So there's your answer. It's kind of a kinematics answer. Now, the algebra here is super simple, okay? And it's going to get us to that exact same spot. I move force of gravity over, and I get force of normal is equal to force of gravity. Okay, Spano, that seems like a whole lot of work to say what we pretty much already knew, that the chair is pushing up just as much as gravity is pushing her down. Yes? But again, this is the work that you need to show on these problems, especially for when problems get a little bit more challenging here later on. So, how do I calculate force of gravity? So we need to take her mass, 68 kilograms, and multiply by g. Now, if this was the multiple choice, I'm going to go ahead and just say 680 newtons. As we're doing a problem, g is going to be 9.8, so let's go ahead and calculate it out. I don't know why it is, today of all days, it felt just like my first hour too, but every year it feels this way, that like I do this stuff up here and people don't copy down what I'm doing, and I don't understand it. Maybe it's because we feel like we already have this intuition, I don't need this. The methodology here, again, I say this at the beginning of every chapter. Hey guys, we're going to start with something simple, so when it gets more complicated, you have that methodology in place. And hopefully eventually you trust me, because that is this right now. It feels like a lot. It does. I get that. I'm doing problems like this with Physics 2 right now, so it doesn't go away. Oh, this is fun. 666.4. That, what we just calculated is her weight. Okay, 666 newtons. That's how much force the Earth pulls her downward. Okay, pulls her downward in order to accelerate her at 9.8. Of course, she's not accelerating at 9.8 because her seat currently, and the seat one in that example, are pressing up at 666.4 newtons. Now, the question that goes along with this is, go, wait a minute, Spainhour, didn't you show something that you said is not always the truth the other day? Didn't you show that gravity and normal are equal? In this case, yes, but we will use another example today where you see that will not be true. Let's move on. So we found force normal. What's next? Force friction. Okay, and if we sum the forces in the y to get force normal, guess what we're going to do? Sum the forces in the x. You got it. Let's go ahead and sum the forces in the x. What are the sum of forces in the x? What are the sum of forces in the x?
Force tension minus force friction.
Cool. Is it accelerating?
Wait.
No, because constant velocity. So once again, this cancels. Equals 0. Telling us that force tension is equal to force friction, which, like I said, we already knew this, right? We already knew it's 9 pounds. Now, that being said, for reasons that I'm going to know that are coming up in the next part of the problem, and also 9 pounds is an acceptable answer. It absolutely is. There's nothing wrong with it, except the problem with pounds is it does not equate when we start trying to do the calculations, because kilograms and meters per second squared are baked into newtons. They're not baked into pounds. So we need to do those conversions. So let's just do that real quick. 9 pounds. I told you the other day that 1 pound is equal to 4.45 newtons. If you don't have that written down yet, make sure you get it written down. 9 times 4.45. Cool. 40.1. And therefore, how much is force tension? 40.1 newtons. And to finally answer Rihanna's question from the other day, Spainhour, how do you know that tension and friction are way, way smaller than force normal? Experience. I knew that the weight, so like these arrows are not anywhere near to scale. If I was trying to make them like legit to scale, they would be like this size right here, and obviously that would be kind of hard to use. So I don't usually worry about that too much, but that is more to scale of what it's supposed to be. I'm not asking you to do that, but that's how I knew. Okay. Now, I told you that we were going to look at two different situations. The first situation was her going at a constant velocity. The second situation was when we actually got started. What was that maximum tug when we actually got started? I actually write it down. What was it? 16 or 18?
It was double. It was 18.
Was it 18? Let's go with 16 for right now. Okay. I don't know. I got my readings. So 16. Basically, when we pulled, this thing came down and hit a maximum. But then I asked her to look at what it was when we were pulling at a constant velocity, and she got that 9. Why is that so much less? Why was it so much less force to pull at a constant velocity? Why did it hit 16 at all? Yes, yeah.
Because it takes a lot more force to get something going than when it's already going.
Why?
Inertia.
No, that's not it. Good try, that. That's a good try. I mean, you go for it, you don't know. Yeah, a little bit, but that's not quite what I'm looking for right here. The main thing I was looking for you to say is that forces have to be unbalanced. Okay, that friction of 40.1, that's probably pretty constant throughout most of the situation. So if friction is always pulling at 40.1 or 9 pounds, are we going to be able to accelerate her if we only pull 40.1 pounds? No, you can see that with someone who's not moving. You can push on them a bunch and they don't actually go anywhere. It's not until you push greater than that amount right there that they actually do start accelerating. Yes, Trent?
I said friction increased with more movement.
So we're getting into static versus kinetic, and we will discuss that when we talk about the models of friction. Absolutely, there is. You are discussing air friction when I said that. Okay. We are discussing currently now the biggest thing here is probably surface friction. In this particular, this air friction at these speeds is relatively zero. Okay. So the question I have now is, how much did she accelerate? We're going to go ahead and assume that this force friction was the same for both examples. How does my force diagram change when she was accelerating at the beginning? Force tension is larger. So what we would do here, okay, to find acceleration is actually, since the sum of the forces in the x is different, I'm just going to sum the forces in the x again. I'm putting it in a different color here to show you this is an entirely different situation. It's an entirely different problem. You would never mix and match these on the exact same problem. But what am I going to do here? I'm going to do the same things that I always do. I'm going to ask the same questions. The first half of this is going to be exactly the same. What are the sum of forces in the x? Exactly what they were over here, at least in terms of variables. I say in terms of variables because the amounts within these variables here, we know in the first case was the same. We know in the second case it's definitely not the same. How do we address that? Right here. Is it accelerating? Yes. So can we cancel it? So if you don't cancel it, you just leave the variables around. Mass times acceleration. Let's do this real quick. I haven't done it yet. 16 pounds. What is that converted to newtons? 4.45 newtons. What is it? What is 60? Somebody punch in your calculator. What'd you get? 71.2. So, again, I'm assuming that friction stays the same. That's the tension because we straight up measured it. I know that to be the case. And do we know what our mass is? So we know that, trying to find that. So we just do a little bit of algebra here. Divide both sides by mass. We get force tension minus force friction divided by mass gives us acceleration, or 71.2 newtons, this one, minus 40.1 newtons divided by a mass of 68 kilograms equals the acceleration.
How did you get the 71 and the 40 again?
71 was the 16 pounds that we measured. Okay. 41, I'm assuming that the friction that from the example that we found over here is the exact same friction that was on you at the very beginning of the situation. So go ahead and calculate what's the acceleration. 71.2 minus 40.1 divided by 68. What do you get? 0.46 meters per second squared. All right, a couple things to address here. Firstly, you will note that this is the first time you actually see mass used in this problem, which once again is indicative of what we said the other day. You don't see inertia actually in first law. Both of these two up here are following first law. How do I know they're following first law? They're balanced. How do I know they're balanced? There's zero acceleration. So if you kind of took this right up here and I wrote it simpler, this would be sum of forces in the x is equal to 0, aka that's Newton's first law. And second law, hey, we divide by mass, we see the object's inertia. Like for example, if I put this exact same set of forces, but instead we used my 2-year-old son, we measured him the other day, he's 31 pounds, which puts him at 15 kilograms. If I do the exact same thing to him with the same force and the same thing here, and it's 15 kilograms, is he going to accelerate the same amount?
No.
Heck no. And you know this. You know intrinsically that if you were to shove my small kid the exact same amount as you shoved Kenzie this particular way, it's going to accelerate a lot more, right? Like she accelerated at 0.46, he's going to accelerate at 2.1 meters per second squared. Yeah, small kids are easy to push around. You knew this intrinsically because it has more mass. All right, let's move on. I'm going to do a problem straight out of the book right now. You're not using your book. I think you're struggling with it. There's a lot of great examples in this book. As a matter of fact, if you struggle on any of the problems from the homework and you do not immediately go to the book, there are so many problems in the book that I straight up just borrow straight out to make sure that that you guys are reading it and checking it, so please make sure you do that. But here we go. We have a rocket sled. Now, a rocket sled is one that is basically a car, but they put it on rails so that it goes straight a lot of times, not always. And it's, instead of powered by an engine, it's powered by rockets. And there are 4 rockets back here. And the question in play is, how much oomph is each rocket, each individual rocket, giving? And I'm going to give that a letter. Since you guys haven't used this at all, we're going to call that thrust, which is, by the way, also another electromagnetic common name. You don't have to memorize this or anything. If ever I give you a new one, I'll make sure and identify it in the problem. We're going to call this thrust. And we'll say that the whole rocket sled with all the rockets and the person inside and the whole mess is 2,100 kilograms, not 210. 2,100 kilograms. We're going to say that we watched this whole thing and the acceleration of it is 49 meters per second squared. And we measure that friction. This is a little bit different from the book because the book get a very small number, and I'm going to make a little bit of a bigger number, is 6,500 newtons. I think the book says 650. So if you look at the book, we're going to get slightly different answers. So, as we do a problem like this, what I want you to identify between the Kenzie problem and this one is that I set up the exact same way every single time, especially if you're sitting there like I have no idea what to do. Listen carefully to the things I'm telling you to do. First thing is, identify your given, and what it is you're trying to find. Within your given, the very next step needs to be a what? force diagram. So go ahead and draw the force diagram real quick, please.
And the T force tension.
No, the T is thrust. In this particular case, it's just the usual letter that's used for a rocket is all it is. Okay, so it's not strings pulling it, it's the rocket pushing it in that direction. But it's
It'd be like the force rock engine on.
correct. Yeah, exactly. If you said rocket on car or something like that, that would be equivalent. All right, let's do the force diagram here. What do you got?
Gravity.
Gravity, good place to start.
Force
Force normal, great place to start. Should be equal, less, or more?
equal.
Equal. How do you know?
It's the rocket is staying on the ground.
Right, it's not accelerating up or down, it's accelerating left or right. Very good. What else you got?
Force
Oh, so it should be equal here. I'm running out of room. Okay, yeah, force friction, where does it go? Backward. Okay, now thrust. You got two options here, okay? But you need to make sure and address it. In the problem, it asks for, it says T is an individual rocket, and it says there's 4 rockets. So what you don't want to do here is you don't just want to be like, boom, thrust. And the main reason why you don't want to do that, it's not that it's necessarily wrong, it's that that T and that T aren't the same in this case. That T is the total thrust. This T here is the thrust of the individual. So your two options are, and I literally don't care, you can either say, I'm going to move this real quick, force normal, go over here. You can either just go 1, 2, 3, 4, okay? Draw all of them individually, all of them there, or if you want, you could just kind of stack them on top of each other and call that 4T. The difference in that case is identifying the total thrust as T versus the individual one as T. Honestly, you have everything you need, so let me give you about 2-3 minutes, see if you can't get in front of me and answer the question, how much thrust does each of these do? What is your next step? What is the next thing we do in these problems?
Find the sum of forces.
Correct. Sum of forces equals mass times acceleration, and in the x. Why in the x and not the y?
Because we're trying to find the force.
Just thrust is in the x. There you go. All right, see what you got. So you should have this, the sum of forces in the x is equal to mass times acceleration in the x, okay? I said that I did left to right for you guys because a lot of people like just going in that standard writing way. I almost always start off with acceleration because it's such a simple thing to do. And just ask the question, is it accelerating? Is it accelerating? Yes, which means we just leave this right side alone and we just transfer it down here instead of canceling it out. The next question, or the first question, is what is the sum of forces in the x? And what should the sum of forces in the x be?
4T minus force friction.
Force friction. Now, this is a good point where I can start to point this out. By saying minus force friction, this is where you're actually addressing its direction. Okay, so later on, when you do the algebra here to solve for t, you're going to add that on the other side. There's a temptation, I think, when you do that to go, oh, I'm adding a negative there. No, you're not. The negative has already been taken care of here. Don't put another negative into that situation. This also comes up with the conversation we said earlier about g. If we go back to that last problem, like you'll notice when we were up here talking about the force of gravity, that g right there is not negative. We don't get a negative answer on force of gravity. How come? Because we're already taking care of its sign right there. All right, the rest of this algebra is pretty simple. We got 4t is equal to that whole mess. So I'm just going to go ahead and divide by 4. And there we go. So the final answer should be 2,100 kilograms times 49 meters per second squared plus 6,500 newtons divided by 4. And this gets a big number. Times 49 plus 6,500 divided by 4, and you get 27,350. Now, there is a temptation that a high school student has with writing every single number in a calculator, because it's more accurate, Spainhour. No, it isn't. It's not more accurate, and it doesn't help. If this is me, here's how I am answering this, and it's probably going to bother you a little bit. Okay, I'm either answering this as 28,000 or 27,400. Why? Because the first one is answering two significant figures. That's actually probably the most logical one due to the fact that if you check the numbers, this number here and this number here, actually no, this number here over here too, all three numbers only have two significant figures. You might argue, no, Spainhour 4 only has one significant figure. No, we counted the number of rockets. That is an infinite number of significant figures because we know there's exactly 4 rockets. There's no decimal place on the number of rockets there. Integers have an infinite number of sig figs. So technically the right answer here is 28,000, but a good rule of thumb, if you don't want to kind of keep track of that, is use 3 significant figures. Now, what a student will tell me, they struggle with this, is they'll go, Spainhour, but when you did this, you added like, oh, I did that down by the way, didn't I? That should be 27,000 if I do my rounding correctly. I saw it and then didn't do it right, my bad, 27,000, rounding down. But yeah, I do this, you lost 350. 350 is a large number of somethings. Compared to 27,000? No, it's not. To put that in perspective, I mean, you guys are probably bothered, I would guess. Some of you just thinking, I don't like it. But watch this. What if the number was this? Same number of digits, I just have the decimal. Are you completely fine with writing 2.7? Is that the same thing? Yeah? Or instead of 2.7, you want to write 2.74? Is that the same thing? Yes. So, when it comes to big numbers, it's more helpful because you don't have to write nearly as many numbers. You can just kind of write zeros, and it's a little bit nicer. And quite frankly, your calculator calculating all these things is not particularly helpful. So like I said, I would choose one of those two answers. And please remember that my calculations on the homework also do that. So sometimes you're like, Spainhour, I got 27,350, but you only said 27,000. Am I that off? No, not at all. All right. Moving on. We're going to look at another situation. This situation is what's known as a cantilever. Okay, a cantilever sounds really fancy. It's really not. Okay, it's a imagine, if you will, like a rod stuck out from a building, and something is supporting it. Okay, a cantilever is basically a structure that's meant to hold something up, but everything is attached vertically as opposed to horizontally like you normally would. The two main ways to normally support this is you either A, put some structure underneath. You can look at this and go, oh, it's like a shelf. Yeah, 100%. Okay, a shelf is a version of a cantilever when supported entirely on the side. Or another thing that you can do would be like attaching a rope or a string up there and coming down and attaching and then hanging something right down here. We're going to go ahead and say that this is like a sign, or like, here you go, I got you. Here's my hand is the rod right here, okay? Just this. Here's the situation right here. Got me? Okay. Draw a force diagram for the cantilever at that spot. We're going to go ahead and say this is 200 newtons. All right. This conversation will take place a few times throughout the class, but I'm going to do it again. I'm just going to do the first one very, very quickly here. So if you don't fully get this particular conversation, I'll tell you when this conversation ends, and you can kind of re-engage. But if I do the force diagram here, this force down is technically not force gravity. That would actually be force of tension. Correct. Now, if you put gravity, it's fine, and I'm going to show you why here in just a second. I just want to make sure that you see what it technically actually is for just a second. It's because of this. What is the force diagram on this mass as it hangs there? Tension which way? Uh-huh. And gravity down. Now, these two are equal to each other. What law says those two are equal to each other? First, because it's at a constant velocity, those two are equal to each other, so tension is equal to force of gravity. These two are equal to each other because of what law? No. Third. Those are the equal and opposites. So, is tension equal to force of gravity? Yes, in this case. Okay? When would that not be the case? Well, here you go. Is tension currently equal to force of gravity on the yo-yo? Yes. What if I do this? Is tension equal to force of gravity in this case? No. Why? Because it's accelerating. And it's accelerating, so force gravity and force tension are no longer equal to each other. And you can feel that, by the way, if you ever have something like this, where you, just like this, okay? You can feel how heavy it is, because you're really feeling tension, right? And imagine you want to accelerate it upwards. What are you going to feel in the string when you do that? What happens to the tension in the string when you do that? It feels heavier. Or if you let it fall and you catch it, does it feel heavier here? Yeah. Did the weight actually change? No, the tension did. The tension did up here. So, if you want to say that tension is gravity in this case, you can see why in this particular case they are equal. It should be 200. That's not what I want to worry about. So let's just go ahead and call that gravity in this case. Also, we're not worrying about the gravity of the cantilever right now, so if you did, that's fine. Don't worry about it. We're just worried about this guy right here. Okay, that's why I said we're going to do it over here. What other forces are on it?
Force tension going half like
Okay. Also, I believe this angle, shoot, I didn't draw it very well. This angle should be 30 degrees. And there's one more force.
force.
It's probably the only time you'll see me do it in this particular class. That one would be force compression. Why? Because the cantilever is being pushed inwards, and it's being pulled inwards, so it's just pushing right back out the opposite way. The question that I have for us in this case is twofold. What is force tension? And what is force compression? By the way, many of you probably have not gotten there yet. This is a straight up homework problem. So, all right. So let's do, if we don't know where to start, let's start up. We only have one force of gravity. I've got my givens right here. So what do I do first? I've got my given, my find, my force diagram. That's first. What's that? Some of the forces in the x and some of the forces in the y. Which one should we probably start with?
Why?
I would start with the y. How come?
Because compression is scary.
No, that's not why. That's not why. It's a good guess. It's not it. Watch it. Because we know one of the forces in the y. We don't know anything in the x yet. Yeah? All right, so here we go. Sum of the forces in the y equals mass times acceleration in the y. Let's start with the easy thing. Is it accelerating in the y? No. It's not accelerating at all, so it's definitely not accelerating in the y. What are the sum of forces in the y?
Negative
Negative ft
Wait.
in the y?
Plus FTY minus FG.
Minus fg equals 0. And of course, we can calculate force of gravity through mg typically, but is this m? No, this straight up is force of gravity. If it tells you the newtons on an object, you don't have to calculate anything. That's the force of gravity right there. So here we go. What do I got? I got force tension in the y is equal to force gravity is equal to 200 newtons. Now, this is why this is helpful. Watch carefully. I know you guys are writing stuff down, and I appreciate that. I did this yesterday. I'm going to do it again. It's super helpful to recognize what I mean by tension in the y. By tension in the y, I am talking about, no, not that. I am talking about this right here, right? Or if you want, over here. How much of that's in the y? That is force tension in the y. Does that make sense? Now, the reason that's particularly helpful is you have an angle. And if you have an angle and a side, do you have every other side? Yes. So, that means I know that this number here is 200 newtons. So what could I do right now to go get force tension? Trig. Now be very careful about where your angle is. I would start to kind of shift your mind definitely away from the cosine is x, sine is y mentality, and much more towards just basic trig. What's my adjacent? What am I trying to go for? Where is force tension on this triangle? The hypotenuse, correct. So what trig should I use to go get it? Cosine. Cosine of 30 degrees is equal to what? (200 newtons) over force tension. Be careful with this. I think way too many people are going to punch into their calculators right now 200 times cosine of 30. If you're not actually doing the algebra, that is not the correct thing. What I regularly suggest people do when doing this is always get rid of the variable fraction first. So what you'll notice here is if I get rid of force tension on the bottom, I have to multiply it on both sides. Then to isolate force tension, I have to divide by cosine 30. So your final algebra should put you at force tension is equal to 200 newtons divided by cosine of 30 degrees. What do you get?
230.5.
Sounds about right. Newtons. Now that knocks out one of them. That knocks out force tension. But now we need to go get force compression. If you're ever confused, here's what I want you to do. I've summed the forces in the y. Guess what I should probably do? Yeah. Is it accelerating in the x? No. What are the sum of forces in the x?
Plus FC
Plus fc.
minus
Oops, I did that dumb. And since that's equal to 0, it's equal to 0. So here's my algebra. That means FC is equal to FTX. Do I know either of those yet? No, but can I very easily calculate FTX with trig? You now know two sides, so the world is your oyster as far as this is concerned. Either use a trig that definitely has the opposite side in it, or use a weird version of Pythagorean theorem. I don't care, but I would probably suggest the trig one. Which trig function you want to use? Can I tell you what I like for your sake? Usually when you do a trig function and there's in two parts, the best thing to do is use the side that was given to you. That way if you screwed up the calculation, like if you accidentally screwed up force tension, you're not relying on that. So I would suggest use this side here because that's given to you. So if we want that, if we have that side and we want this side, what should we use? Tangent. So I'm going to write tangent of 30 equals the opposite, which is force tension in the x, over the adjacent, which is 200. Now in this case, again, it's so funny to me how similarly trig looks sometimes, but it isn't. Like here, because of the switching, we had to kind of divide, but over here, yeah, you can just divide by 200 on both sides, and force tension in the x is going to equal 200 newtons times the tangent of 30 degrees. And that's going to be that. What do you get? 115? Is that right? Is that what you said?
7.5.
Did you just give me a bunch of decimals after the conversation I said a minute ago? 3 sig figs is all I'd worry about if I were you. Yeah, 115. All right, I have one final small problem. And that small final problem is to address something about force normal and about Newton's first and second law. Right here I have a water bottle sitting on the desk, and here I have a scale. Now the key thing I want you to understand about a scale is a scale does not inherently measure weight. It doesn't. It doesn't measure weight. It measures the spring force, because they almost all use springs. So that being said, I could do what you guys all expect me to do, okay? I could hold it up like this. What is the force diagram on that guy right now? You can either say tension or spring, I don't care. Force tension going which way? Up, agreed, and gravity down. Now, as I hold it here, what do you know about those two forces? They're equal. Why?
Because there's no acceleration.
Because there's no acceleration. But watch this. Is it accelerating now?
Yes.
Is the spring force the exact same as it was before? No. You pull off this exact same effect if you stand on here. You stand on a scale, okay, and you don't actually want to know your weight, you can bounce up and down. Does the scale read what your weight is? How come?
Because you're putting more force.
That's probably what I'm looking for. You're not wrong either, though. I'm putting more force, but I am accelerating. Because I'm accelerating, we know they are unbalanced in both cases. Okay? Now, one last thing is this. I hold it up, it is 4.5. So what does that mean about the weight of this? It's 4.5, right? Those are equal in this case. But what if I put it on the table? Notice how it gets a little bit less. I'll hold it right here at 2. Why can it be at 2 right now?
Because there's a force.
This is force normal. Calculate, do the force diagram on this right now. Remember, weight of this is 4.5 and this is 2. Do the force diagram on this and show me what force normal is. And I know, again, you can probably do it in your head, 3.5. But show the work like we've been doing today to show what the force normal is on this particular situation. Once again, your givens are, we know the weight of it is 4.5 by holding it up like this. And I set it down until the scale reads 2. When the scale reads 2, what is force normal? Go ahead and do that work. Do the force diagram first. Ooh, before I forget, I'm going to run out of time here. Tomorrow we have a lab. The lab is large. Okay? Takes a while. Explaining it takes a while. Those both don't fit in the same class period, and I want it done in one day. We really need you guys to watch the intro video that I made in years past. So it's like a 20-minute video. If you have time tonight, try to do that. If for some reason you don't have time, at least read over the lab before tomorrow. But ideally, everybody in your group watches that video so it's easy peasy tomorrow when we get started. Yes? Sure. I'll finish this problem when you guys leave here in just a second. So if you want to like flip the video to the very end, if you want to check it out. Okay, so let's finish that problem. So if the canister here is pulled upwards by a spring, okay, and we know that that reads on it 2 newtons, and we've already figured out that the weight of the object is 4.5 newtons because that's what the spring said when it was completely suspended. The question is, it's on a table, what is force normal? And you begin with the force diagram. The force diagram looks like this. We have force gravity down, force tension or scale is pulling up, and then we have force normal also pointing up in the exact same direction. So to find force normal, we would sum the forces in the y equals mass times acceleration in the y, and start with those exact same two first questions that we usually do. It's not accelerating at all, it's just sitting on the table there. The forces acting on it are threefold. We have positive force tension, positive force normal, minus force gravity, and because of this, it's all equal to 0. Then we do a little bit of algebra. I'm going to add this one on the other side, so that's positive force gravity. Subtract that one on the other side, minus force tension. And so we get that force normal should equal 4.5 newtons minus, I think I've been saying the wrong answer all day, minus 2 newtons. I think I keep saying 3.5, but the answer is 2.5 newtons. In other words, that tension pulls the opposite, tension pulls the amount, normal pulls the amount, my apologies, that tension's not making up for. So if I pull a little bit harder and a little bit harder, then force tension will get bigger and force normal will get smaller, and they will still equal force gravity. And there's still going to be force normal until tension takes the full 4.5 newtons up, because the thing weighs 4.5 newtons down. So that's how you do that.